Welcome! This video is a walkthrough of the solution to problem 1 on the MODS 2020 April Beginner Contest, which was held on the 11th and 12th of April. The problem reads, find all triples x, y, z of non-negative integers such that 2 to the x equals 3 to the y plus 6 to the z. To help us get a grasp on this problem, let's try some small cases. We'll list some powers of 2 and draw an addition table for 3 to the y plus 6 to the z. On first glance, it looks like most values in this table are odd, but the only odd power of 2 is 1. Indeed, if z is at least 1, then the left-hand side of the equation is the sum of an odd and an even positive number, which is itself odd and greater than 1, so there are no solutions here. That means z has to be 0, so that both sides of the equation can be even. These lists have 2 and 4 in common, but they don't seem to share any other values. Well, for a number greater than 1 to not be a power of 2, it has to have prime factors other than 2. So let's explore the prime factorization of the other terms. Looking at their factorizations, it seems like some of the terms are divisible by 2 but not 4, and the remaining terms are divisible by 4 but not 8. And what's more, these terms seem to alternate. In fact, if we could prove this conjecture, then the problem would be greatly simplified because the left-hand side would have to be a power of 2 less than 8. So let's try to prove that no term in this list is divisible by 8. To prove such a statement, it can be useful to consider the remainder of each term upon division by 8. So let's take this list modulo 8. Indeed, this reveals another alternating pattern, and we can prove this much more easily. We note that in mod 8, 1 times 3 is 3, and 3 times 3 is 9, which is congruent to 1 mod 8. And the cycle repeats, 3, 1, 3, 1, and so on. Then adding 1 to each term gives us the desired result. Thus, the right-hand side of the equation is never divisible by 8, which means that the only powers of 2 that can work are 1, 2, and 4. But we already know that 1 doesn't work, and that 2 and 4 have one solution each. And that means the only solutions are 1, 0, 0, and 2, 1, 0, which finishes our proof.